there is a comforting idea we rely on, that even if we don't understand everything, we understand enough to classify planets, enough to predict outcomes, enough to know what is possible and what is not. Extreme worlds challenge that comfort. They exist at the edge of our models, where predictions become uncertain and assumptions begin to fail. At first, we treat them as errors, data, noise, temporary phases, outliers that don't deserve too much attention. But the more extreme worlds we discover, the harder it becomes to dismiss them. Because they don't behave randomly, they form patterns we can observe, but cannot fully explain. They persist where collapse is expected. They stabilize in states we thought were temporary. They evolve in directions our simulations don't predict, and that reveals something uncomfortable. The problem isn't that these planets are strange. The problem is that our models assume the universe prefers simplicity. They assume systems move toward balance, toward stability, toward predictability. Extreme worlds do the opposite. They sit at the edge. They resist equilibrium. They survive chaos, and when enough of these worlds exist, they stop being anomalies. They become evidence. Evidence that our understanding is incomplete, not because we lack data, but because we rely too heavily on frameworks built from limited experience. We learned planetary science by studying calm systems first. Now we are encountering systems that were never calm to begin with, and the rules that worked before are no longer sufficient, which leads to a dangerous realization. If we don't fully understand how extreme worlds behave, then our predictions about the universe are only accurate within a narrow comfort zone. Outside of it, we are guessing. And that raises a question we rarely ask out loud. How many things do we believe are impossible simply because we don't yet understand how they persist? Planetary models are powerful tools. They allow us to simulate how planets form, how they evolve, and how they respond to forces over time. But every model is built on assumptions, simplifications that make complex systems manageable. And most of those assumptions come from one place: experience. We learned how planets behave by studying systems that were already calm, already settled, already stable. Our models were designed to explain order, not chaos. So when we simulate planetary evolution, we assume systems move toward equilibrium. Heat dissipates, orbits stabilize, atmospheres thin out or settle. Extreme conditions are treated as temporary disturbances, short phases that systems pass through on their way to balance. But extreme worlds expose the weakness of that assumption, because many of them are not transitioning. They are persistent. Their extreme states last for millions, sometimes billions of years, which means our models are not predicting reality. They are predicting preference. They describe how planets tend to behave under ideal conditions, not how they behave when those conditions never existed. This becomes a problem when multiple extremes interact. Most models isolate variables. They change temperature or rotation or atmospheric density one at a time. But extreme worlds rarely change one thing at once. Their anomalies stack. A strange rotation affects internal heating. Internal heating affects atmospheric chemistry. Atmospheric chemistry affects heat retention. Each anomaly amplifies the next. This creates feedback loops that traditional models struggle to represent. Instead of damping instability, the system sustains it. And because these interactions are nonlinear, small changes early in a planet's history can lock it into extreme behavior permanently. That's not a flaw in physics. It's a limitation of our simulations. We prefer clean inputs and predictable outputs, but the universe does not. Real planetary systems are messy. They reinforce extremes. They settle into configurations that look wrong only because we don't simulate them well. So when a planet violates multiple expectations at once, we label it an anomaly, not because it breaks physics, but because it breaks our assumptions. This is why extreme worlds feel unsettling. They don't fit into the categories we rely on. They don't behave like early-stage planets. They don't behave like stable planets. They occupy a middle ground that our models were never built to handle, and that creates a dangerous illusion. We begin to trust our simulations more than our observations. When the data disagrees with the model, we assume the data is flawed. But extreme worlds are forcing us to confront the opposite possibility, that the data is correct and the models are incomplete. Incomplete models are not harmless. They don't just limit what we understand. They shape what we believe is possible. When we rely too heavily on simplified frameworks, we don't just miss anomalies. We misinterpret reality. Extreme worlds reveal this risk clearly, because when a planet doesn't behave as expected, our first instinct is not to question the model. It's to question the planet. We call it unstable, temporary, an outlier, and then we move on. But if those labels are wrong, the consequences are larger than a single misclassified world. They affect how we interpret the universe as a whole. If our models assume that equilibrium is inevitable, then any system that resists it looks broken. But what if equilibrium is optional? What if persistence doesn't require balance? In that case, entire classes of planets may be systematically misunderstood. Not because they violate physics, but because they operate under conditions our models were never designed to explore. This creates a dangerous feedback loop. We design models based on what we already understand. Then we use those models to decide which discoveries deserve attention. Anything that doesn't fit is treated as noise. Over time, our confidence grows, not because our understanding is complete, but because we stop looking where our models fail. Extreme worlds break that illusion. They force us to confront the limits of prediction. They remind us that the universe doesn't owe us simplicity, and that matters beyond planetary science. Because the same assumptions shape how we think about stars, galaxies, and even life itself. If we assume that complex systems always move toward come states, we will underestimate what can persist under pressure. We will overlook systems that thrive in imbalance. We will misjudge longevity. We will misunderstand resilience. This planet, and others like it, exist at the edge of our confidence, not because they are rare, but because they expose how narrow our expectations are. They don't tell us that our science is wrong. They tell us it's incomplete. And that distinction matters, because incomplete understanding is not a failure, unless we mistake it for certainty. Extreme worlds remind us that prediction has limits, that models are tools, not truths, and that observation must always outrank expectation, which leads to a final realization. The most dangerous assumption in science is not ignorance. It's misplaced confidence. And as we continue to discover planets that resist explanation, the real question is no longer whether these worlds make sense. It's whether we're ready to accept that the universe is under no obligation to fit inside our models. In the next video, we'll explore what happens when confidence collapses and how new discoveries force science to rewrite its own rules.